So, welcome to Module 12, Troubleshooting. Now, as I said earlier, we basically are just recapping this section. So, as we went through all the configuration steps in previous chapters, we addressed common troubleshooting issues dealing with that topic at the time. This module is basically just summarizing all of that again and presenting it. But it also adds a little bit more to it. So in this one, we're also looking at maintaining network documentation, how to develop it, and how it's used within troubleshooting. We'll go back over the various methods used in systematic approaches to troubleshooting. We'll look at the various tools available to us. Then we'll go through some common symptoms and causes of problems, and then recap some basically troubleshooting processes. So documentation plays a very important part in networking. Now, unfortunately, this is the least maintained part of networking. So our physical and logical network topology diagrams are important for us to understand how components go together. And it's generally one of the first documents we reach for when we try to troubleshoot a network. The next document we need to concentrate on are our network device documentation, which records individual information about each device, such as what their interfaces are, what their MAC addresses are, what their IP addresses are, what protocols are running out of each interface, that sort of information. Next, we'll look at how important it is for us to have a very robust baseline document. This will give us a good understanding of our true performance of our network over a period of time. These documents should be like anything else. They should be copied and stored in multiple locations. So, in other words, we need to back up these documents just like we do tape backups and so on for our network data. We should treat this information with the same due care as we keep for the information we're in charge of protecting on behalf of the company. So the physical diagrams, as you hopefully remember, are about giving us physical characteristics. So it should be pretty much the same document as you can see here, but the type of information we have on them is different. We'll have where they're physically located, so what building they're located in and what room, and then what equipment rack and what shelf in the rack they're located, as well as their physical interfaces and how they interconnect. Now, compare this with our logical topology, and what we're showing is still showing the interfaces, but we're showing the IP addresses and the VLANs that run over our networks. So this tells us all the logical information we are required to have so that we can understand how to piece it together. Now, what's missing from this is the associated tables of VLAN information that runs on switch 1 and switch 2. Because the other thing we need to know is what ports are allocated to each VLAN on all the switches. We need that to be able to configure them. So we need to have that information as well. Generally speaking, it is in a table format, just like it's shown there, but on each switch, just like the labs documentation that you see. So you can break that down into the individual device documents, which should be kept up to date. And these are examples of how you keep that. So you have your basic table of your device, your model, your description, the location, what version of operating system it's running, and what licenses are applicable to that device. So you then go through and list all your interfaces, give a description as to where it connects to, what the IP addresses are, what its individual MAC address is, and what routing protocol it's running out of that interface. This allows you to rebuild any missing information as needed. You rinse and repeat for all your various types of devices. So the next example here is on a switch. We have the port numbers, the description of what it's connecting to. So in this case, it's a trunk. And then it will tell you what port channel it belongs to, if it's a part of a ether channel or whatever version of you're running. And it'll tell you what the native VLANs are across those trunks. And the other ports will tell you whether they're in use or not. And if it's an access port, what VLAN it is, and whether it's shut down or enabled. Then the last document is your end devices. So this is where you go through and list your servers and your desktops. Rinse and repeat. So device name, generally you'll have a asset tag number, so you can keep track of what you're documenting on top of what's shown here. So that's important to note as well. Then what operating system it's using, what services are provided by the server, what its MAC addresses are, its IP addresses, and its gateways. So where it's part of a network, what is its gateway, what is its domain name address. So as you can see, it's a complete picture in table format of all your devices on your network. Now, as you can imagine, this is a horrendous task to do from scratch. That's why it's very important to maintain these tables as we go, because that way you'll get to only do minor modifications as you add and swap out equipment. It's very easy to maintain this equipment by just dedicating 5 minutes at the end of the job to go in and update these documents. Okay, you go through and you do a whole plan on how you're going to deploy the equipment, what configuration changes you need, get approval for the maintenance window to make the changes, and part of that planning should be updating the associated documentation. A lot of people forget about it and don't do it, so they fall out of date and become fairly irrelevant, and then some poor sod has to eventually go around and totally rebuild them from scratch because they're so far out of date that they're no longer usable. And this comes to a head when there's a major problem. When you're doing disaster recovery and you're going, well, that's not very often. No, it's not. But I've worked in 2 companies over my years that have gone through full data recovery because of fires in their main establishment. Okay, so their main office burnt to the ground. Now, how do they rebuild things? Well, they had documents kept on site in a fireproof room in fireproof safes. And guess what? Some of those documents still came out scorched. So this is why it's important to follow these guidelines of keeping your documentation secure, as well as your backups of working projects. And it's important to keep them backed up locally and off-site. Okay, so I can't stress this enough. The next thing you need to establish is a baseline. So this gives you what they call the personality of your network. It establishes what the traffic patterns are under normal operating conditions. You can then use this information to forecast and plan upgrades, because you can see where congestion is starting to occur and what will happen if more users are added. Those congestion points will build. So you can do some forecasting and planning based around this simple procedure. So how do you go about it? Well, you start by selecting a few variables that you want to capture, and these need to represent and be defined by networking policies. If too many data points are selected, then you get overwhelmed with so much information, it's near on impossible to do a productive analysis of that data. So start out simply and start fine-tuning it as you go. So you'll find out if you're missing information, and you can just add variables in and you can start to build a data set together. Good starting points are always interface utilization and CPU utilizations. So this tells you how hard your devices are working. Next, you need to identify these devices within your topology. So you just highlight where you want to capture the information from, so what interfaces, and then you can define your ports of interest. So from this topology here, you can see they're capturing the main interfaces in use. They're using the outbound interface towards their ISP, their interface towards their server, and then coming down to the branch, they don't need to collect it on the central interface. They can collect it on the branch one, because we're already collecting 3 points of interest from central. We can share the load a little bit. And by doing this, we can build a picture of, okay, well, if this is being utilized here and it's having so much traffic port through it, we know it's coming in on central. So we know what percentage is balanced across all the interfaces by the various access points. Collecting switch 1 allows us to have an understanding of what switch 2 is doing, because to travel anywhere out of the branch, you need to come up through switch 1. So we're getting aggregated results. And the same occurs over at branch 2. We're getting aggregated results coming up through the branch router. So we need to define the period that we're going to run this collection over. Now, the longer, the better, within reason. a minimum of 7 days, so you capture every day of the week, and you shouldn't be more than 6 weeks. Normally 3 or 4 weeks will give you a good picture, but you need to repeat this yearly because your network will have changed considerably over the 12-month period. I haven't seen very many networks that have remained static over a 12-month period. You may not have added many physical devices, but your user traffic certainly changes. As the company's priorities change, so will their traffic patterns. So you need to conduct this regularly. It doesn't have to be a full network analysis. You can just start isolating sections of the network to collect your data on. This way you don't overload any given section of the network, and you can update and build more effective views of your network. So one of the things you could do is just isolate where your changes have been occurring and use that as an update point. Okay, so you update where your main changes have occurred, use your collection points around that and capture the main bottleneck points, and then update that data into your old baseline, and you'll see any relevant changes. So how can you go through and get information and collect data? Well, you can use the show version. This will tell you how long the device has been up and running, what version of software and hardware it's running. You can show the interfaces. This will give you statics on the interface. It'll give you the MAC addresses, the IP addresses, all that lovely stuff. Your routing table will tell you what's connected, and then if you wish, you can break that down into your routing protocols and segregate it out that way. Your layer 2 discovery protocols, so CDP or LLDP, will give you directly connected devices, so you can build up any gaps in your topology diagrams. Your ARP and neighbor tables will also help you understand how your devices are communicating with each other. Your configs, how often have you made a change and not saved it out and backed it up properly? Your VLANs will give you a list of what active VLANs are on any given switch, and the show port status will tell you what ports are doing what on the switch. Now, the last one, be very careful with this one because it dumps a large amount of information, and it's used for technical support reporting generally. But you can use it, but be aware it's going to dump a lot of information, and while it's collecting all of this and dumping it out, it's going to use CPU cycles. So if this device has large CPU utilization to begin with, by running tech support and this type of large information gathering type process can have adverse effects. So back to a very basic troubleshooting process. Talk to the people, find out what the problem is, i.e. gather the symptoms. Try to isolate the problem, implement a correction action. Did it fix it? Yeah, great. Document the solution, save your changes. If it didn't fix the problem, undo the change, because you don't want to create another problem and then start again. Now, there's lots of different ways of going through the solutions. That one was a 3-step solution. Here's a more detailed 7-step process. Again, we need to define the problem. We need to gather the information, analyze the information that we have gathered, go through a process of elimination and eliminate potential causes, come up with a possible solution, test whether that actually resolves the problem, and part of that testing process is to have a rollback plan if something goes wrong. When the problem is resolved, you can then document and save your information and inform the appropriate parties that the problem has been solved. So part of that is to ask the users pertinent questions. You should try to, let's say that again without having to clear my throat halfway through. You need to ask open-ended questions. The reason for this is you want to give the people you're talking to the lead for them to be descriptive in their answer. If it's a closed question, you're basically asking them to give you a yes/no type answer, which isn't in itself very informative. So you need to ask them what they were doing when the problem occurred. Get them to define exactly what it should be doing. Okay? Work out the scope of the problem. Is it only affecting a single device, or is it affecting multiple users? When did the problem occur? When was it first noticed? Was there any changes that occurred before the problems surfaced? Find out if it's constant or intermittent fault. And if it's an intermittent fault, your challenge of resolving it has just escalated skyward. Determine what's changed, and that's what asking them if anything's changed. Now, a lot of users won't know whether anything's changed or not, or they just may not think it's relevant to tell you. All right. The purpose of this questioning is to try to eliminate or define the problem. So the users, for the vast majority, are only concerned about technology when it doesn't work for them the way they want it to. Most officers and things like that won't even notice a person working on a device until it doesn't work for them. Just a word there. So after gathering information from affected users, you can start using some simple commands to see if it's a connectivity issue. So if the device is on, you need to find out whether it's still communicating with the rest of the network. So you can do ping, trace routes, telnets, in other words, remote access. Then look at appropriate IP addresses, try to find out whether it's a routing problem or whether or not the actual protocols are being supported. Now the last one is useful. Debug. All right, all these show commands just give you a snapshot of what was happening at that precise time. Excuse me. It will not tell you of changes as they occur. The debug does. So, to give you an example, OSPF. It can appear to be configured correctly, but the process may have stopped. One of the reasons a process stops with OSPF is if one of the routing IDs has become invalid, and that will stop the routing process. You won't get any hello packets going back and forth, but when you do the show commands, it looks like it's all running. Because none of those show commands are going to tell you whether the hello packets are still happening or not. So by turning on debug IP OSPF, you can see whether the packets are being sent and received. So you might be receiving, but you may not be sending, things like that. Only the debug command will tell you what's going on. Remember to turn it off. Once you've done your diagnosis, turn the debug off because it's very resource hungry. Now, you need to understand where your devices sit within the OSI models. Now, we need to know this because the characteristics of problems will depend on where they sit within the OSI stack as well. So we've got a varied range of troubleshooting approaches that we can use. Now, the two main ones that were taught to newcomers is bottom up or top down. This is a systematic, layered approach to troubleshooting. Then after a while, as you get experience, you'll start doing a divide and conquer. Sort of jumping in the middle because you're not going to check to see if the lights are on. A ping command will tell you what's going on or not. So you kind of jump in the middle and try to do a couple of commands that will eliminate which top end or bottom end where the problem is. Follow the path. If you've got a traffic problem, you'll try to follow the path along the network to find out where the issue occurs. Traceroute is a classic example of a tool used within that method. Comparing non-operationals with operational elements is very useful, especially when you're doing configs troubleshooting for tunnels. As we've said previously, tunnels need to be configured exactly the same at both ends, barring their destination addresses. So doing a comparison between both ends of the tunnels, if possible, will quickly eliminate any potential configuration mismatches. The last one, educated guess, really only comes about with experience. And the one that listing there that is not shown is you will generally be part of a team of support people. Ask your colleagues. Some of those colleagues will have been around a lot longer and have seen a lot more than what you will have. So after you've tried to do something and you can't resolve the issue, rather than spending hours or days trying to figure it out, you ask your colleagues and go, I'm stuck. What do you think could be a possible cause of this? And they will step you through possible solutions. So how do I work out which way to go? You need to determine the type of the problem, you need to analyze the symptoms, you need to, do all of these things on the fly. So which method should I use? Depends on your skill and what information you're getting told. If it's software-oriented issues, then you should really use a top-down method because applications are at the top of the OSI stack. So a top-down method is explicit. If they're talking about hardware issues, well, maybe you should use a bottom-up. If you've got a fair bit of experience about troubleshooting, you might have known experience, seen it a few times, so you can use a divide and conquer method because it eliminates half the OSI model and you can concentrate on what you believe is a narrower scope of potential. If it's something you've not seen before, maybe using a bottom-up method would apply. So in other words, select your troubleshooting method based on your experience and the information that you're getting from the users. So what are the key tools? Well, network management system tools will monitor devices and give you feedback on possible changes within the network. These tools can be used to investigate and correct minor issues. Knowledge bases are what companies like to build. Okay, these are generally an online database of known issues that they've come across and their symptoms and their solutions. For businesses, this is an invaluable source because they're combining all the knowledges and experiences of their employees into this knowledge base. Less experienced people can use this knowledge base to help eliminate potential causes and come to a high probability solution with less work and less downtime. Baselining tools allow us to create automated capture of information, which we can help build documentation from. And with good base documentation, such as network diagrams, we can update these documents quickly and easily. And we can then use these to build pictures of what's going on. Now, I'm not necessarily talking about topology diagrams and things like that. I'm talking about your understanding of how the network works, where the traffic flows. Depending on the company's applications in use, where their servers are located, you need to understand where the normal traffic flow resides. Because when you come to troubleshoot, you need to know that stuff. You need to know what's normal, what's abnormal. Protocol analyzers such as Wireshark capturing software and others of its ilk. Wireshark is one that we reference because it's free. There's a whole range of other software tools available to us that we can download and use off the internet. These have been developed over years by companies, and most of them will have a free version and a paid version. just with different tools available to us. So what we can do is filter the traffic and capture specific types of information. Now we can then analyze these protocols and what's exactly going on by expanding their headers and looking into their payloads, because if they're a protocol, it's well-known structure, and you'll find port information, valid checksums, what type of request it was. You can see all sorts of information. The addresses being used. Now, what if we need to diagnose the actual hardware? The cable. We can use multimeters if we really need to. That will tell us whether we've got current and voltage, especially if they're providing PoE, whether we've got the right resistance. I personally prefer to use dedicated cable testers and analysis tools because they're smart tools. You can plug them into the cable and see what's exactly going on. And they'll tell you whether there is improper shielding between the strands and whether you have crosstalk going, whether there's a break in the cable, approximately where it is away from you in meters. They're very useful. Excuse me. Next, we have analyzers. Now, depending on the scope of analysis we want, we might have handheld ones that are really good for, certifying our copper cabling and fiber cables and that. And then we might have to have a portable network enabler, which is a standalone unit that specializes in troubleshooting switch networks. So it'll delve in and try to find out any issues within the switch network. Now, we have Cisco Prime NAM. Now, this is a browser interface application that allows us to perform analysis over the entire network. There are other vendors that do exactly the same thing, but as we're doing a Cisco-sponsored course, they're going to promote their own product. We've seen the Syslog server configuration and where we would use it. And remember, all devices have this ability to generate event messages. When we turn logging on, we also have to tell it what level of alerts we want to be notified about. Now, our console will display level 6 messages, informational by default. Okay, you can change this to any of these levels. So the lower the number, the higher the severity level of the message. And as we hopefully remember, the outputs of these messages will be in a template form, so they all can be analyzed. And what we've got to remember is when we turn logging on and we want to collect them for analysis, we need to put timestamping on as well, so we can analyze events as they occur to work out what the lead up to the event was. Potential system issues. So this is where it's going to go through symptoms layer by layer. put a description against the symptoms, da da da. This is going to be a huge wall of text. I'm only going to pick out one or two on each slide. Otherwise, we'll be here for hours going through it line by line. Basically, the key ones are loss of connective. It's pretty obvious. Check to see whether the device is still plugged in, power still turned on, and use your ping command to find out where something's occurred. Okay. Most network devices have indicating lights on it. So if you've got green lights, you've got a circuit. All right. You might get degrading in performance if you're getting congestion on your network. So you're going to have a higher drop rate, more lost messages, that sort of thing. So what you've got to do is look at what's happened to cause that increase of drop rate. It may be a faulty link and your network's trying to reroute traffic around the issue. Okay, network layer. No, they're still on physical layer. Yeah, they're going to have lots of them. All right, attenuation. What's attenuation? This is where the signal degrades because we're trying to send it too far. I've seen lots of people pull in cables more than 100 meters long and go, oh look, it still works, it's fine. But what's not going to work is the fact that you're going to have more collisions on that stretch of cable. Why are you going to have more collisions? Because the time it takes to send the frame is much longer as it travels along. So while you're sending it from one end of the cable, the other end of the cable thinks it's clear to send because the distance is too far for it to know that there's another frame being sent. You could also have corrosion occurring on any of the joins in the cable. Noise, this one I like. I saw a very clear indicator, which you won't see these days, of electrical AMI. Okay, back in the day we had CR monitors, so cathode ray monitors. They had a large magnet on the back of the cathode to direct the stream of information being projected from the back. Now, if you were unlucky enough to sit next to the lift well, every time the lift went up and down, if it wasn't a very well shielded motor, every time that lift went past your workstation, your monitor would go haywire as it degaussed, and none of the electrons would line up neatly on the back of the screen, and you would get some very funky psychedelic images, just to give you an idea of what happens when that occurs. Moving up to the data link layer, we have again all the issues with needing to know what your baseline is, because if your network performance is degrading, you need to have that baseline to compare it against. Next, excessive broadcasts. Generally this happens if things are not managed correctly. So if you've introduced a new program, it may not be programmed efficiently, and it's flooding messages out onto the network that don't need to be there. I've seen this a few times. There's some very poor coding out there that's being sold for money. Just look at Microsoft, to say nothing of the others. And other things like mapping issues. Now, you're going, how can there be mapping issues? Well, there's a finite number of combinations of addresses that a vendor can stamp on their network cards. And if a vendor has an issue where their counter stops counting between product on the production line, you'll get a whole heap of products going out with exactly the same address pre-configured on them. And when you put those brand new cards into the network on the same segment, you have two versions, two devices saying they are the same address. This may cause you issues. I'm pretty confident to say that yes, it will cause you issues because I've seen it. Just putting it out there. Now, one that you may not also come across very often these days is framing errors. One of the reasons for creating framing errors is loss of integrity. So the clock on a serial line might come out of sync and you'll get faulty transfer of information. Moving up to the network layer, we may have a failure that causes productivity to be lost, such as a routing issue, congestion, or there's lots of things that can there. The issue with the network layer may not specifically be with the network layer. It may be a result of something else, because if something going on in layer 1 or layer 2, it's obviously going to affect layer 3 as well. Neighbor issues, not getting updates from neighbors, not forming adjacencies for the protocols. So there's lots of issues that we've talked about previously. As I said, not going to go through them all. Transport layer. Biggest problem in the transport layer is where we've got misconfigured ACLs. All right. Your ACL goes from specific to general entries. If you have a general statement before a specific statement, it'll match the general statement first because it's sequential as it comes down through the list. And first match is the one it actions. Be sure that you have them applied in the right direction. Make sure you're using the correct protocol and port numbers. NATs, well, there's all sorts of problems here. You will have some very interesting issues with NATs and ACLs and tunnels. What you need to do is get a good understanding of your device, because each of these features are applied in a specific order. So you need to know the order of operation to help diagnose these issues. So if you have a ACL on an outbound interface and it's got NAT running on it, then that filter may not be being matched because the address is being translated before it hits the filter, for example. Or your NAT may not be working because you've got an inbound filter that disposes of the information before it gets to the NAT engine that tells it it's allowed through. So this is where it becomes interesting. Applications, well, don't get me started with application issues. This is why I like working with routers and switches, because if I've got connectivity, then I can pass it over to the admins team that looks after the applications, unless it's one of my management tools. Then I tend to get a little unstuck and have to deal with it. All right, so again, a lot of the issues for applications tend to occur when we use these in conjunction with some other feature that we've turned on. So a lot of issues with applications come about from ill-conceived filters. So again, misconfiguration on filters can lead to application failure. Because if we do not explicitly permit traffic through a filter, it's denied. That means everything else that we haven't explicitly permitted is denied. So if you're writing it and adding a line for a specific issue and you haven't permitted anything else, well, guess what? You've denied everything else by default. So stuff that was working now isn't going to work because it's been dropped, and you'll get some irate calls. Now, to recap, bottom-up approach allows us to go through to determine end-to-end connectivity by checking whether physical activity is happening. All right, are the lights flashing? Are the lights on? You would be surprised at how many times we did final exams with live equipment where I just turned off a switch and people couldn't troubleshoot because they would not check that the power was plugged in. Okay, we've all seen the memes about IT support and people not turning on monitors and things like that. They're real. Sadly, they are real. And people starting out in this industry also make those types of mistakes. Duplex mismatches, links going up and down is the symptom. So they can't agree on the circuit. Potential address mismatches throughout the network. Not being able to talk to our gateway to get off our local network to the wider network, internet, for example. Tracing the path to make sure we have connectivity between the source and the destination. Now, tracing the path may allow us to get from point A to point B using ping or trace route, but that doesn't necessarily mean that a particular application will successfully get from point A to point B. It just means we've got connectivity for the ping command. So if we've got connectivity and we still can't get an application to run, then maybe some form of filter is blocking our traffic. If we're using domain names, which 99.9% of the stuff we do, we translate URLs to IP addresses, let's check to make sure that translation is actually occurring. So, what do we do? PC1 needs to talk to the server. So the first thing we should do is ping to see whether we get there. If we don't get a response from server 1, maybe follow it up with a trace route so that we can see whether it goes through router 1, router 2, or router 3. Because you'll get a notification saying it's arrived on router 3, but then you may get a notification saying that the network is unreachable after that. So what this does is gives you a starting point for further investigation. How can I track it down? Well, you start using your show commands. See if there's any errors in the queues or in and output, CRC checks, that sort of thing, whether there's collisions occurring. See how many drops are occurring. Maybe it's congested and it's getting a lot of traffic, so it may have lots of drops, lots of errors. Next, have a look to see whether our speed and duplex settings match up. Because one that's set to full duplex and one set to half duplex will not talk to each other. Check to see that our address is being matched up with a physical address. Remember, we need a pair. We need an IP address and a MAC address of the device we're sending the frame to, because the device needs to know to pick it up at layer 2 before it can action the information in layer 3. If you have VLANs, check to make sure your port numbers are assigned to the correct VLAN. You may have made a typo, or somebody else may have made a typo, and in this instance here we have an interface that is telling us that it's on port VLAN 1 and it should be on VLAN 10. So it's a fairly quick fix. You go into the interface, switchport mode access, switchport access VLAN 10, problem solved. Misconfigured default gateways will be a problem. You won't be able to get off your network. So this is where our pinging of our gateway and doing trace routes will tell us whether we're getting off our network and how far we're getting. If we have, as in this case, PC1 has a default gateway of router 1. Router 1 has a gateway of last resort, which is router 2. So router 1's address is 192.168.1.2, which points to router 2. How do I verify this? From PC1's perspective, a route print or a netstat -r, and in the case of the router, show IP route. These commands can be used in both versions, IPv6 and IPv4. Alright, you know that the difference between the command structures that we use are basically just the IP and IPv6. So one of the issues that a lot of people forget about when they want to use IPv6 is it's not on by default. So you need to turn IPv6 unicast routing on to get routing occurring. Just as, yeah, a little word. So verifying the path, you need to check whether the destination address is in the routing table. If it is it pointing in the direction that it needs to travel in? If it's not, do you have a default route? If it is, follow it to its default location, the next hop. If it hasn't, it's going to drop the packet. Remember that. If there's no entry in the routing table, the packet is dropped unless you have a default. If you have multiple entries that would match the destination IP address, you need to look at the longest path. All right. Verifying the transport layer. Well, a quick and easy way of doing that is if you've got administrative rights to the devices, you can remote access in. Telnet SSH are applications. They run at layer 7. So if you can telnet to the device, guess what? You've got full connectivity and you also have application level. So one of the cool things you can do with Telnet is actually specify the port number. By specifying and changing the port numbers that you want to use, you can check whether your ACL is blocking the application or not. Because remember, we filter on IP addresses and port numbers. So that'll tell you whether or not it's getting held up by an ACL. Next, you can check where the ACLs are applied and in which direction they're applied in. Are they applied on the correct interface? Are they applied in the correct direction? These all affect connectivity. Next, we need to confirm that we have connectivity to our server for domain name translations. And the other thing we need to check is whether we're getting responses from there. And we can use the NS lookup to get the mapping information. We can use the IP host command to create our own DNS entries on our devices. We used to do this quite a lot in the earlier versions of the courses. One of the reasons we would create these individual DNS entries on devices is so that we can ping the device's name. Like we would create an IP host R1 and then list the IP addresses associated with R1. That way we could ping R1 and it will rotate through those addresses and allows us to get away with not remembering all of those addresses all the time. And if you're trying the telnet or doing some other remote access, every valid IP address on a router is a valid entry point for remote access. There's some troubleshooting packet tracer activities associated with the chapter, please complete. Alright, so there's a couple more to do. And using documentation to solve issues. So quickly recap. We explored how important documentation is to network troubleshooting and how we should keep it up to date. We recapped on troubleshooting process. We also looked at a few different tools that can be used to gather information and solve issues with knowledge bases and baselining tools, so on and so forth. Then we had a look at various common issues based on their layers. Now, I strongly recommend you go back and retouch these, because as new individuals to troubleshooting, it's always get a good idea from these chapters of how issues present, because this is your introduction into this new field of troubleshooting. So these guidelines will help you build your skills. Okay, as my mentor told me, and I've told many of my students, I cannot teach you troubleshooting. I can only teach you the guidelines to troubleshooting. Troubleshooting comes with experience. You need to develop and hone those analytical skills and problem-solving skills by yourself. I can't teach them. It's a matter of how you approach and a particular mindset. Then we went through a couple of scenarios talking about bottom up, top down, divide and conquer, and lots of other different issues associated. Now, all of these were a repetition of the symptoms and elements of all the previous configuration chapters that we've covered throughout all three courses of the CCNA learning material. We are on chapter 12. We have 2 more modules and you've finished all of the current version material for version 7 of the CCNA. So it's pretty important that you wrap it all together and be able to pull all those separate little elements together and start presenting it as a unified front. So this is why these summary chapters have been put in. That brings us to the end of Module 12, and I'll be turning on the next round of combined chapter exams, which I believe is from chapter 9 or 10 through to 12, so it's 3 or 4 chapters in this group for this chapter exam. I'll turn that on, and then the task for this afternoon will be for you to complete your revision process of these chapters, complete the packet tracer activities, and then do the chapter exams. Any questions? The usual. Okay.